Hello again, this is another video on Lewis structures. From what you've seen so far in chemistry, you will have seen that chemistry is all about rules. Rules for this, rules for that, rules for the other. But the fact is, although chemistry is a lot about rules, for every rule there are several exceptions. So chemistry is almost all about exceptions rather than rules, because there's a bloody many of them. And the octet rule, unfortunately, is just one of those things where there are exceptions. We said before that with the exception of hydrogen, every atom wants to achieve its octet, so it's 8 outer electrons. So when we do something like carbon, nitrogen, oxygen, for example, fluorine, these all want to achieve their 8 electrons. But there are situations where there are atoms that don't actually have to follow that rule at all. They can just say, well, bollocks to that rule, I'm going to do what I want to do. Sort of. Let's have a look, for example, at BeF2. Now, Be is beryllium, very small atom in the periodic table. And let's just count up our valence electrons the way we have done before. Beryllium is in group 2. It has 2 valence electrons. Fluorine is in group 7. And so that's 14, so giving us a total of 16 valence electrons. Okay. Now beryllium with two valence electrons looks like this. It can form 2 bonds. Fluorine, on the other hand, 7 valence electrons. So let's draw these out. 4, 5, 6, and 7. So fluorine usually forms 1 bond. So therefore that would suggest the central atom is beryllium. So let's draw that out. So here we go. There's a beryllium, there's fluorine, there's a fluorine, and we've used 2, 4 electrons so far. Now each of the fluorines, we'll do the outermost atoms first, and that's the common way to do it. You fulfill all your electron requirements of your outermost electrons using lone pairs. That should be a bloody hell. Sometimes this software likes to say, you're not drawing a lone pair, I'm going to screw with you. I'm going to draw a line instead. Okay. How many electrons have I used now? 2, 4, 6, 8, 10, 12, 14, 16. I've used all the electrons I'm supposed to. I've fulfilled the requirement of bonds for beryllium, and I've also fulfilled the requirement of bonds for fluorine. Now each of the fluorines has its octet of electrons, but beryllium doesn't. Now it turns out this is actually the valid Lewis structure for BeF2 or any beryllium salt. Because of the fact beryllium only has 2 valence electrons, it only has space for 2 bonds. So if you were to ask yourself how many bonds or how many electrons are actually around beryllium in this complete Lewis structure, it's actually only 4. And that's correct. Beryllium is just too small to accept anything else. And let's do the same thing here. Boron is in group 3. And chlorine is in group 7, and there are 3 of those. So we add all those together. Alright, now if we just do exactly the same thing, boron has places for 3 bonds, and chlorine actually is in the same group as fluorine, so if we just fill up to 7 electrons here, we'll see each chlorine can usually form 1 bond. Chlorine can actually form more, but for right now we're just going to assume chlorine can form 1 bond. So that would tell us then that boron is the central atom. So let's draw on these. Chlorine, fluorine. We'll put our single bonds between them, same as we always do. And then, just as we did for the fluorines, we're going to draw on our lone pairs to complete the octets of each of the 3. Wow, 3 times in a row. Alright, Now, let's count up the electrons now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. Hang on a minute. I can't count properly. I have 3 bonds, that's 6 electrons, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lone pairs, 20. No, I don't. I'm sorry, guys. It's too early in the morning, too late in the morning. Whatever. I have 9 lone pairs. That's 18 electrons plus 6 electrons in bonds, giving me 24 electrons. So I've fulfilled my number of electrons here as well. Notice though, it's the same thing as for beryllium, well, almost. Boron, because it only has 3 lone pairs or 3 valence electrons, it can only have a total of 6 electrons around it, even though that's a valid Lewis structure. So these two are the atoms that can violate the octet rule by having less than 8 electrons around themselves in a valid Lewis structure. And then we go to the other side of the coin, where we can have more. H2SO4. Sulfur is in period 3 in the periodic table. It's big. It can actually accept more electron density around itself because it's got higher energy empty orbitals, as all bigger atoms do. But without getting into too much depth about that, let's count up our number of valence electrons here first. I have 2 from the 2 hydrogens. I have 6 from my sulfur, and I have 6 from my oxygens. I got 4 of those though, so that's 24. So I actually have a good number of electrons to place here. That is 32. Okay. Now, let's think central atom. Okay. Oxygen is in group 6. So that's what the atom, that's what our oxygen valence electrons look like. Sulfur, also in group 6, is the same thing, but there's a little bit of a giveaway here. There's 4 oxygens and 1 sulfur. So which one do you think is the central atom? Well, more than likely it's sulfur. So what we've got to do is to find out a way to arrange those 4 oxygens and 2 hydrogens around the sulfur. So I think, well, I don't know, what if I put an oxygen here, an oxygen here? You remember what we said, and that the hydrogens are always going to be on the outside? So I'm going to do something like this, and then think, well, if the hydrogens are on the outside, then maybe the hydrogens are connected to the oxygen, perhaps. But let's just try something like this first. Let's draw connecting bonds to the sulfur and the oxygen. Okay. Now at this point it looks like we have completed our our octet rule requirement for sulfur, because we have 4 bonds around there. But that's going to pose something of a problem for our oxygens, because we only have 2 hydrogens to add on here. So if I put a hydrogen here and say a hydrogen here, then I get to a point where only 2 of my oxygens have complete octets when I put my valence electrons on. But let's just have a look at this and see what it looks like. How many electrons have we used so far? Well, we've used 1, 2, 3, 4, 5, 6 bonds, so that's 12 electrons that we've used, meaning we've got to place another 20. Well, all we're going to do is to go around the atoms that are necessary and add on whatever lone pairs we need. Because at this point, I don't want us to think about any other extra bonds. Okay, so if I put lone pair here, and do the same thing for my other oxygen that's got 2 bonds, and then when I come down to these oxygens, each of those oxygens only has 1 bond, so they need 6 more electrons. So I got to place these here, and these here, and these here. Now, if you add all these up, that's 8. That's 16, that's 24, that's 32. I've actually used all my lone pairs. So you could argue this is a valid Lewis structure, and it actually is, it's just not the best one. And the reason why is formal charge. The formal charge on each of these oxygens, we saw this in a previous video, is -1. Because oxygen has 6 valence electrons, -1 bond connected to it, plus 6 lone pair electrons, giving a total of -1. Now this molecule is overall neutral, and if I have 2 negative charges, I've got to have 2 positive charges there too. And they're not coming from the hydrogen or the oxygens, it must be from the sulfur. But let's see. Sulfur is in group 6. How many bonds does it have to it? Well, it has 4 bonds to it. And how many lone pair electrons are on the sulfur? Well, that's 0. And that means the sulfur has a formal charge of +2. Now this means this is extremely unhappy. It's very, very rare to see a formal charge of bigger or smaller than -1 or +1. So this should tell you, oh dear, we have a problem. Is there some other way we can connect all our atoms together to not have this S+2 here? Well, it turns out there is. And it actually doesn't involve us doing anything different in terms of how everything's arranged. I'm just going to draw out my atoms again in exactly the same way they were drawn before. Okay. I'm going to draw my bonds like so, just like we had before. Now we want to ideally get rid of these 2 minus charges, because if we get rid of those 2, we'll also get rid of this +2 as well. So if we ask ourselves, oxygen, it wants its octet, and it can achieve that by either adding 3 lone pairs or adding another bond here. And if we go from a single to a double bond, it looks something like this. This double bond then gives the oxygen its required 2 bonds, and means therefore we only have to complete that octet by adding 2 lone pairs rather than the 3 we had here. And if we do that over here, well, maybe we can do it over here as well. So we put those on there. I'll put my other lone pairs on oxygen that I did before over in the other structure, and we get something like this. Now what you're thinking right now is, hang on, what on earth is going on here? I thought you said all these guys had to achieve 8 electrons. Well, you know, the title of this video is Violating the Octet Rule, and as I said before, sulfur, along with phosphorus and anything above it, chlorine, bromine, whatever, all the other bigger atoms, sulfur has a bunch of large of high energy empty orbitals that electrons can go into to allow it to form more than 8 bonds. In fact, sulfur can form up to, I think it can actually form up to 6 bonds around itself for 12 valence electrons, and which is what we have going on here. But let's see what that does to the formal charge, and you'll see this is actually something interesting and perhaps unexpected. Look at the oxygens here. Valence electrons is 6, minus 2 bonds, plus 4 electrons, 0. And if this one is 0, then this one's also got to be 0. This and this are the same as this and this here, so these are already 0, which must mean then that if everything else is 0, this sulfur must be 0 too. Now you might not have thought so, but let's just count up the valence electrons then, okay? Let's do the formal charge, sorry. Sulfur has 6 valence electrons. In this case it's got 6 bonds to it, no lone pairs, so therefore the formal charge of sulfur is 0. So this is the best formal charge for sulfuric acid, because there are no formal charges, even though the sulfur is violating the octet rule. Okay? It's exactly the same process. I'm not going to go through this in detail, but it's exactly the same thing for something like PCl3. When you think about it, sorry, not PCl3. Excuse me. Again, it's still too early in the morning. PCl5. Because phosphorus really should only be able to fit 4 chlorines around it. 5 means for some reason it's able to pack 2 more electrons around there, and again that's because phosphorus is in group 3, in period 3, sorry, and it has those empty orbitals where extra electron density can go. So you'll see, particularly for sulfur and phosphorus, there are cases where the best Lewis structure is one in which those atoms have violated the octet rule. Okay.